Hey, this is Jason Molesky. In this example, we'll construct a one-sample t-interval for mu. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675, and the standard deviation was 0.3332. Let's construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. Well, in this case, we'll have to start by checking our conditions to see whether or not we can use a one-sample t-interval to estimate mu. We note we do have a random sample. The data were stated to come from a random sample of 40 engines from the population of all light-duty engines of this type, so this requirement is met. We're sampling without replacement here, so we need to assume that there are at least 10 times 40, 10 times the sample size, or 400 light-duty engines of this type. Seems reasonable to assume that. Now, we don't know if the population distribution of NOx emissions is normal, but because our sample size is large and is equal to 40, which is greater than 30, we should be safe using a t-distribution, so our large sample size condition is met. So with that, we can proceed to constructing our interval. From the information given, our sample mean was 1.2675, and our sample standard deviation was 0.3332 grams per mile. Now, to find the critical value t star, we'll use the t-distribution with degrees of freedom 39, one less than our sample size. Unfortunately, there's no row corresponding to 39 degrees of freedom in the table. We can't pretend to have a larger sample size than we actually do, so we're going to have to use the more conservative, smaller degrees of freedom of 30. So, setting up our formula, we'll take our point estimate, x bar, plus and minus a critical t, times our sample standard deviation divided by the square root of n. Plugging that information in, we find our interval is 1.2675 plus or minus 0.1076, or more precisely 1.1599 to 1.3751. So we are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. Now, if we were to use technology with our